Welcome to SanfordFlipMath. This is AP Calculus. We are continuing to work through the Finney, Demana, Kennedy book. We are in chapter 6, about halfway through, a little more than halfway through. This is section 6.4. It is about exponential growth and decay. What we're going to be doing is basically focusing on finding solutions for differential equations again. And it just turns out that they happen to be exponential functions, like a numerical base to a variable power when we're done with it. So that's really it. There's not a lot different in this section than stuff we've already been doing. It's just how things tend to work out is the big takeaway. So we're going to start by working through this initial value problem. And remember, this is just a differential equation, and solving a differential equation means finding y equals. That's what we want. What we currently have is dy dx equals, and that's not what we want. Okay, so we're going to solve this thing for y, get rid of the d's and all of that. Okay, so first thing we need to do is separate the variables. So notice I have y's on both sides, I have x's on both sides, and that's not terribly useful. So I'm going to multiply. I guess we could cross multiply. So I have y dy equals negative x dx, and all I did was cross multiply. Don't forget the negative sign. Excuse me. I got to put that back. Come on. Oh, all right. Well, there we go. Okay. So I want the d's to go away. So let's do a little antiderivative action here, and the antiderivative of y is going to be y squared over 2. And on the other side, antiderivative of negative x will be negative x squared over 2. And there needs to be a plus c in here somewhere. And at this point, we need to solve this thing for y. And as it stands right now, it's got y squared and some other stuff going on. And honestly, I don't really need these fractions here anyway. So I'm going to multiply both sides by 2. And something's going to come up here that you're not going to like. And I'm going to apologize for it, but it's part of calculus. This little guy right here is 2 times a constant, is still just a constant. And I will tell you that in most calculus classrooms, they will play pretty fast and loose with these c values. And so they'll replace this 2c and they'll just call it c. Just so you can keep it straight, what I'm going to do is I'm going to kind of call this c1. And you don't really have to do this. You can just call it c. Because it's just going to be a different constant, but I guess the issue is it's a different constant. So it's still a c. We don't really need 2 times c. You could leave it 2 times c. There's just not a reason to, really. Okay, we're almost done. We need to do y equals, so I would prefer to call that y, that instead of y squared, we're going to take a square root of both sides. Okay, and so what I'm left with now is y equals plus or minus the square root of negative x squared plus c. Now, I know some of you are concerned that that's negative, but remember that, because you can't take the square root of a negative, that opposite of x squared. And when you square x, it's going to be positive, but keep in mind that you're going to be adding that to some other number, so don't get all freaked out about it, okay? We're basically done with this, except we need a value for c. So let's take our x and y. It says y equals 3, so 3 equals. Do I really need the plus or minus anymore? I mean, this is clearly a positive number, and the answer from a square root would be positive all by itself. I'm not going to have the negative there. So for this particular initial value, it's going to be the positive. So I'm not going to worry about the negative. It's just going to go away. Negative 4 squared plus c. So 3 equals, this is negative 16 plus c. And now I'm solving for c. So I guess we'll square both sides. 9 equals negative 16 plus c. And so we'll add 16 to both sides. So 25 equals C. And all right, so for those of you tracking along, those are really C2s. And now it doesn't matter anymore because we're just going to put it in the equation. Okay, so this was y equals the square root of negative x squared plus 25. Most people are going to prefer that to be written, excuse me, something like that. Now, I mentioned to you that we were going to have exponential functions. This is not an exponential function, but it is solved kind of the same way we've been doing, and so this is, and it's going to come up in this section, so we'll go ahead and deal with it now. So this is an initial value problem. It's dy dx equals, our goal is y equals, and the initial value, 4 and 3, lets us solve for the c. Okay, let's move on. Okay, so here's another initial value problem. Obviously, this already has some exponential stuff going on in it, so we're going to have to play with it. And the big issue that I want to point out is, notice the x and the y are in the exponent. So this particular one, we're going to have to kind of rewrite this. And so I need to remind you that when you are subtracting exponents, that really means division. So we're going to have to rewrite this dy dx equals, and it's going to be e to the x over e to the y. So that's a little different, okay? Well, from here, it's going to kind of track out kind of like what we did a minute ago initially. Remember, I want all the y's on one side, and they're across the equal sign like that, and all the x's like that. So I'm going to go ahead and cross multiply. Okay, so I'm going to have e to the y dy equals e to the x dx. I have separated the variables. You have to separate the variables first. If you don't separate the variables, it's going to get all jacked up, and you can't separate the variables later, because really what I'm going to be doing right now is antiderivative to get rid of all the d stuff, dy, dx. And when I do antiderivative, I have to do with respect to the variable in that little d. Okay, so this thing has to be about y, or I'm going to be throwing a y in there that doesn't need to be there. Okay, all right, so the antiderivative of e to the y is really just going to be e to the y. And the antiderivative of e to the x is e to the x. Now, just a reminder that when you do this, if it would have been e to the something x, like for instance, if it would have been the antiderivative of e to the 2x, that would have been e to the 2x over 2. So if there's a number involved in there, make sure you deal with that number appropriately. Okay, now this doesn't say y equals yet, which is kind of annoying. So the question is, how can we make this say y equals? So how about, since I want the y by itself, how about I rewrite this in log form? So I'm going to write log base e of all of this equals y, equals the exponent. Remember, the log equals the exponent. Okay, so I'm going to kind of pull it over here. Okay, so y equals ln e to the x plus c. Sorry, got to squeeze some parentheses in there. Okay. Okay, so what I want to do is kind of pop back. See, I'm looking at this right now and I'm saying this is not in acute form for me to do a lot of work with. So what I'm going to do is I'm going to go ahead and substitute and see what's going on. I have, that was funny. I have x equals 0 and y equals 2, so 0, 2 is my ordered pair. I'm going to go ahead and put this in right here, or I could put it into this one. You can substitute and find your c at any step along the way, provided you have already done the antiderivative, because the antiderivative is when you get the plus c. So I actually think I like this one better. Okay, so off to the side here, let me just kind of rewrite, and this doesn't feel very organized to me, so I'm sorry. But I'm going to grab that, and I'm going to put in place a y, the 2. So this is e squared equals e to the 0 plus c. And e to the 0, or e to the second is just e squared. E to the 0 is 1. So c is going to be equal to e squared minus 1. Okay, and I know some people just got mad because I flipped it. So for you, I will flip it back. Okay, so this is going to be e squared minus 1 equals c. Okay, so going back to this, y equals ln e to the x plus c. Well, that's rather disgusting. But that's what it is. Okay. All right. So I want to go next to another example. This example is kind of the meat and potatoes of the exponential stuff, and but we had to kind of review and deal with some of the scariness that comes up on the other stuff. Okay, so I'm going to start out the same way. I'm going to isolate the y's with y's, isolate the x's with x's, and I will say that this 3, it doesn't really matter whether you leave it with the x's or with the y's. I'm going to leave it with the x's on the right side. So I'm going to multiply both sides by dx, divide both sides by y, or you can think of it again as cross-multiplying if this is over 1. Okay, so let me not block all that. Okay, so this is going to be dy equals 3y dx. Divide both sides by y. So this is going to be dy over y equals 3 dx. Now, to get rid of the d's, as is always the case with solving a differential equation once you have the variable separated, I need to do integral or antiderivative, but the issue now is, what's this dy over y? Now, some of you I know recognize this. I'm going to write it one more time, so I'm not really doing any math here. I'm just rewriting it in a different form because I need you to recognize it. And I'm going to pull this 3 out because I need you to recognize what I'm doing there. So at this point, the 1 over y should be screaming at you, oh, that's natural log. Okay, so antiderivative of 1 over y is natural log of y, and a reminder that the absolute value has to be there because we don't know whether whether y was positive or negative, and in order to make the domain of 1 over y fit the domain and range for natural log, I have to make that positive because I can't take the log up a negative. Okay, 3 times antiderivative of dx is just x, and I got a plus c in there. Okay. If I had an initial condition to work with, this would be a great time to put it in and solve for c. I can wait, or I can do it now. I don't have an initial condition for this, so I'm just going to leave it plus c, but I don't have y equals yet. So how do you get rid of a log? Well, rewrite the form. So this is going to be the base. The base for natural log, as you recall, is e to the exponent. Remember, logs are exponents, so this whole thing over here on the right is the exponent equals the absolute value of y. Okay, I'm going to pick it up over here. So solving for y, in other words, getting rid of the absolute value, well, oops, sorry, biffed. E to the 3x plus c. Yes, that plus c is in the exponent. You need to be careful to keep it in the exponent. Okay, so back to getting rid of the absolute value. Well, this could have been the inside of this could have been positive. The inside could have been negative. So I need a little plus or minus when I undo that. And I will tell you that I am fine with this form. This is fabulous. If I had an initial value, then I would have substituted in before, and it would have dictated to me whether this was positive or negative. Okay, I will also tell you that most books, tests, etc. will not leave it in this form. Instead, they will remind you something like, all right, so I have this plus or minus. When you are multiplying, you add exponents, so this is the same thing as e to the 3x times e to the c. So this is now going to be, I'm going to write it 2 more times. E to the c, that's a c, sorry, that's an e, that's a c, times e to the 3x, and one more time. Okay, what's that a? It's just another constant because this is ugly. No offense. So this is typically how you'll see this left. Well, what about the plus or minus? Well, it's in the A, because it's not going to be both. So it's either positive or it's going to be negative. Okay. So one of the things I want you to notice here is this started out 3 times y, and notice this is 3 in the exponent. Okay, so I want to do one more just like this, and then we'll be done, because this is kind of like the catch-all. Okay, so ky. So this is some constant times y equals, and again, solving the differential equation means I want to know what the original function was that we took the derivative of. Okay, all right, so I'm going to kind of buzz through this. The steps look just like what I just did. It's just instead of a 3, it's a k, and it confirms the format, that little thing I was trying to show you a minute ago. Okay, so I'm going to multiply both sides by dx, divide by y. Okay, I'm going to do the antiderivative of both sides, and I know I'm booking here, but time is my issue, and it's going to look just like what I just did. Okay, the antiderivative of 1 over y is ln of y. Don't forget the absolute values. And this is going to be kx plus c. Again, we're trying to get y by itself, so this ends up, and I know I'm not going slow, and I'm sorry, e to the kx plus c equals absolute value of y. Okay, so y equals plus or minus. And again, I'm going to break up this multiplication. So this is kx times e to the c, rearranging. Okay, and again, usually, I mean, all of this is one big number. So usually people rewrite it like this. Now, if you do this enough, or if you drill this enough, now this is one thing that comes up every now and then. I don't think it's worth memorizing, but the fact is that some people do. That's what they do. They just remember that d by dx equals ky. Oh, that's that exponential thing. That's a times e to the kx, and they just remember it. Okay, so again, if there was an initial condition, you could put it in your x and your y here and solve for a, and that would be your constant. You could solve for the c way back here, and based on, if you had a number for k, and based on that number, you would eventually calculate a. It's up to you how you want to handle that. All right. We're calling it good. This is 6.4, again, from the calculus course, AP Calculus, and thanks for hanging with me. Sanford out. Bye.